So welcome to the third in a set of slides designed for additional study resources for the upcoming test, Test 1. I want to again, I know you've heard it before, but I really want to reiterate that these are not meant to be an exhaustive and complete listing of everything that's going to be covered in the test. The test is being drawn from all of the lectures, all of the slides, the homeworks, somewhat a little bit of your assignment and the lit reviews you've done. But also from the text readings as well, which are meant to supplement what's been going over in class. These are mainly presented as just a summary of some of the key concepts, some of the harder equations, and just as a quick way to review some of the material that's on the study guide. Again, the better standard for what you need to know to do well in the test is everything that's on the study guide. So I want to talk a little bit again about reliability. So again, reliability is just the consistency in measurement. Sorry for that, my chair is squeaking. I'm not sure if you're picking that up or not. But it's consistency in measurement. So again, reliability is our first step in trying to determine how well a measure is working, especially if we're actually getting at what we think we're getting at, which is, in this case, a stable construct. So if we have a reason to believe that what we're measuring is stable, it's a trait, one of the first things we want to check with our new measure of that trait is whether it's reliability. And we're going to do this generally by creating a reliability coefficient. We're going to basically do correlations. And depending on how we test for reliability, we're going to use different methods to get that coefficient. And again, correlations are simply we have two variables that are both interval or ratio, and we're seeing how highly they're related. And this builds on the idea of what I've talked about in class, the idea that TS, or true score, is always not just observation, but observation plus or minus error. So what we're trying to figure out is how much error is in our observation. Now, what it isn't telling us is whether that observation is actually getting at the construct we're interested, our true score. That's validity, and we're going to test that in different ways. So error refers to a component of the observed score that does not have to do with the test taker's true ability or the trait being measured. And again, a strong reminder that true score equaling or not equaling observation plus or minus error is a theoretical equation. We never know what true score is. But we do know the less error we have, the more likely our observation might be closer to what that true score is. So measurement error is all the factors associated with the process of measuring some variable, other than the variable itself being measured. So error is everything that a measure is capturing that isn't actually the construct we're interested in. And it's kind of hard to get rid of all error because it's hard to really determine what all could be going into that error. And some of it might not even be things we can easily control. So for instance, though personality is a fairly stable trait, it does fluctuate from time to time. And various interventions and events that occur in our lives will have momentary or somewhat lasting effects on our personality. Measurement error, though, is when we actually have problems with the way we're actually measuring in the first place. And we can do a fair amount to try to make sure that we have less measurement error in our measures. And that's another way to increase reliability. So, just some measures of reliability. We talked about briefly Cohen's kappa. Cohen's kappa is a way to actually measure the reliability of independent judges that are watching behavior to assign ratings. So basically, if you have multiple clinicians making a clinical determination of whether someone is clinically depressed, if you've got multiple raters deciding if someone should get a job or not on a yes-no, if you've got multiple raters that are deciding if someone's boxing performance was winning or losing, you use Cohen's kappa to determine how often, statistically, are those raters agreeing and how often are they disagreeing. And what we're wanting to see is those raters, if they're reliably rating a construct, they should be fairly in sync with each other. They should agree more than they disagree. And we kind of talked about in class also that Cohen's kappa and most of these measures of reliability, we're often wanting to see at least approximately a 0.7 or higher on that R. And Cohen's kappa isn't an R, it's a kappa, but it's the same thing. It ranges from 0 to 1, with 1 being perfect agreement. We also talked about other ways to get at reliability. One is test-retest. So we have our test, we give it to people, we wait a little while, and we give it to them again. That gives us our two variables that we can now run a correlation on. And then again, we look at the correlation. If that R is above 0.7 or higher, we can say this test seems to be fairly reliable. We can also use alternate forms to get the two variables that we need to look for the comparisons. In this case, we're actually going to create two different tests from a larger pool of items that are meant to measure the same construct in the same way. Again, we give people both forms, they take them both, and then we make the correlation to see how well they're related. We also can use split half internal consistency. So in this case, we take a test, we divide it in half, and we use the first half against the second half. So they're only taking one test with split half. But if it's 20 items, maybe we compare in a correlation all the odd items to all the even items, or the first half of the test to the second half of the test. Again, the stronger those items correlate, the stronger an argument is being made that it's a reliable test that's measuring the same thing. We also briefly talked about Kuder-Richardson. That's a technique that we use when the outcome isn't interval or ratio. It's actually dichotomous or categorical. And again, it's a way to look for reliability in that type of a test. Now, the problem with the split half internal consistency is it's the easiest to do. So if we take a look at these middle three, test-retest requires us to test people twice with the same test, and it also requires us to do it over a period of time. Alternate forms requires us to actually make two full versions of the test out of multiple items. Split half allows us to take one test and administer it once and still look for reliability. But the problem is that we're dividing the test in half in order to run a correlation, which means if we use a split half internal consistency, we actually need to do a little bit of an adjustment, and that's the next slide. And that's the Spearman-Brown formula. And what the Spearman-Brown formula allows us to do is actually look at what the consistency of a test would be if it was longer or shorter. So the equation here, the very first box at the top in blue, the blue box at the left top, R subscore SB is what we're calculating. So that's going to be the new Spearman-Brown correlation after the adjustment. The NR XY that's N by R. So R is the actual value that we found as far as reliability in our split half test. And N is what we're trying to calculate as far as what the next test would be. So if we wanted to know, for instance, we ran a split half test, what the R should be in a longer test, N in that case would be 2, because the test should have been twice as long as the test that we actually used. We had a 20-item test and we broke it into 10 and 10. So that correlation is based on 10 items. Well, the real test is twice as long, so N would be 2. If we have a 20-item test and we want to ask the question, what if we cut it in half? What if we dropped half the items? In that case, the new test would be half as long, and we'd use the same equation to estimate what would the reliability now be by using 0.5 where N is. So anywhere we see an N, we put in the value of what the test would be, and it's a proportion based on what the test currently is. And wherever we see an R with the little XY subcategory, we put the reliability of the current test. So in this case, we had a reliability of 0.8, and we want to ask what happens if we cut that test in half. So the top of the equation becomes 0.5, cutting the test in half, by reliability 0.8, and the bottom of the equation becomes 1 plus 0.5, cutting the test in half, minus 1, multiplied again by reliability. Now, I'm not going to walk through the rest of the equation, but basically we calculate this out and find out that in this case, that if we actually took a test with a reliability of 0.8, which is good, but cut it in half, our estimated new reliability would be 0.67. It actually would be lower, and it's probably below that 0.7. We might not want to do that to that particular test. I'm sorry, I probably should have been clicking these forward while I was talking, but here's the examples of going through the math and that final result. So again, the N is going 0.5 and the RXY is 0.8. So another thing we can look at, and this is one of the go-to tools, is again, if we have interval or continuous data, so continuous data being both interval and ratio, either one, we can also, with multiple items, as long as they're all on the same scale, do a Cronbach's coefficient alpha. And what this is doing, it's comparing every single item in our scale to itself, but it's not having to break it apart like it was with a split half test. It's comparing every single item to the average of all the items and to every other item. And it's actually doing Spearman-Brown corrections in the equation itself. So as it does this, it's making the corrections for the fact that it's looking at smaller samples as we break this apart. At the end, it then averages all of those correlations to come up with a single alpha, which is still a correlation. So 0 means absolutely no consistency. 1.0 would be perfect consistency. And again, 0.7 or higher is usually considered pretty good consistency. And this can again be done on a single test. So we don't have to give multiple tests like test and retest. We don't have to come up with alternate forms. We can actually just use a single administration of a test to a large sample to look for how reliable is that test. So the other neat thing about internal consistency using Combrex Alpha is we also get information about which are the good items and which are the bad items, which means we can also then go, if we don't have quite as much reliability as we want, we can isolate individual items to remove. And when SPSS runs this, as we did in the lab, we actually get a fairly nice readout that we can take a look at and see actually how well that represents what should be pulled out of the items. So just as a reminder again, that generally speaking, we want to see it with Combrex Alpha at least a 0.7. 0.8 is considered very strong, and 0.9 is actually considered necessary if you're actually going to make clinical decisions with your actual internal consistency alpha. So right here, I actually have an example of the SPSS readout. Just a reminder, the main thing we're interested in is that alpha. That, in this case, it's not very strong, 0.32. Remember, we want at least a 0.7 or higher. But what we also get in the far right of the item total statistics is for each individual question, what the alpha would be if we remove that item. So if we go to question 6 and we go over to that green box, we actually find out if the question 6 wasn't included, our alpha would go from 0.32 down to a 0.17, much worse. So that's one of our best items. However, if we look at question 10, we actually see that that one, if we remove that item, the scale actually gets better. It goes from 0.32 to 0.417. That's a bad item that we'd actually want to remove. I also want to talk about the standard error of the measurement for a moment. Just quick calculations here. So again, standard error of the measurement is an interim step that we use calculating both the standard deviation and the reliability of a test to find out how much error is in the test. Now again, SEM is a midterm equation. We need to calculate it for what we're really interested in, which is confidence intervals. So for example, if we have a standard deviation of 0.75 and a reliability of 0.8, we simply put them into the equation. So the 0.75 goes where the omega is in the symbol, so standard deviation, and the reliability goes where the R is. And then we just run through the equation. So 1 minus 0.8 inside the square root sign becomes 0.2. The square root of 0.2 is 0.45. We calculate or multiply 0.17 by 0.45. We get 0.34. That's our standard error of the measurement. But now what we want to do is we want to put that into a confidence interval statement. And confidence interval is giving us the plus or minus off the observed score that we have 95% certainty that someone's score actually falls between. So in this case, our SEM was 0.34. The second part of the equation is always a standard. It's 1.96. So 0.34 times 1.96 is 0.67. Once we have that, you can take any observed score from this sample and add or subtract 0.67 to get the range of what is the 95% confidence interval. And what that means is that you're 95% certain that someone's true score is falling between that range off their observed score.